Am I audible? Please confirm if you can hear me. So welcome to the week 3 of fundamental algorithms. If you're not able to hear me, then please let me know. So in week 3, we have seen a couple of topics. Specifically, we had seen these lectures, a lecture on red-black tree, a lecture on augmented data structure, one on computational geometry, one on Emde Boas data structure, and dynamic programming. So there are a couple of questions on these topics that we are going to discuss today. So let's go to the first question first. So we have seen a red-black tree. So I'll let you read the question for a minute and then we can discuss. So what is the first property of a red-black tree? Anybody? Is red-black tree a balanced binary search tree? So what do you think? Hello. Yes, Hari. All right. So red-black tree, as we have seen in the videos, is in fact a balanced binary search tree. So therefore, its height is order log n. So height is order log n, where n is the number of nodes, the total number of nodes in the red-black tree. So you know that the number of nodes and the number of internal nodes are of the same order. That means the number of leaves and the number of internal nodes are roughly same. So it is also true that if n is the number of internal nodes, then the height is going to be order log n. So of course, option B cannot be correct. And option D also cannot be correct. I mean, option B is definitely not correct. Option D is also, it's an overestimate. It's an upper bound. The correct answer is either A or C. So which one is the correct answer, you think? A. So we've got an answer from Gahan that A is the correct answer. So yes, so we have seen in the videos. So if you look at the first video, if you go through this lecture 11 red black tree, then in this video it has been derived that this formula, that is the height is at most 2 times log n plus 1, it has been derived. So we'll go through. I hope that you have watched the videos. So it's been derived in detail that why this is true. So that's why the correct answer is A. All right. So let's look at the second question. So you have to understand what the properties of the red black tree. So what is the so let me tell you. Uh, in this balanced binary search tree, yes, Hari, you have something to say. Okay. Yeah, so we were talking about red black tree, which is a balanced binary search tree. So every node in the balanced binary search tree, which is a red black tree, gets either the red color or the black color. Every node is colored either red or black. All right. So what is the color of the root node? What is the color of the root node? Anybody? And what is the color of any leaf node? You have watched the videos, I believe. So it's the first thing that is discussed in lecture 11. Any guesses? There are two options only. Either it is red or black. So we have seen that the root node is black. Also, each of the leaves is also black. What else have we seen? We have seen that if a node is red, then its parent should be black. Okay. These properties we have seen. These are by definition. So now you can answer the question. You can try to answer the question. So you have a red black tree on n nodes, and you want to ensure that the number of red internal nodes is as much as possible. See, the red nodes are not leaves, so they are definitely internal nodes. So you want to maximize the ratio of red internal nodes to black internal nodes. So basically, you want to maximize the number of internal nodes that are red. Then which of the following should be correct? Consider option B. Each red node has two red children. Is this possible? It's a binary tree. It's saying that there is a red node and it has two red children. Is that possible? So consider the third property. If there is a red node, then definitely its parent is black. So how can a red node have two red children only? That's not possible, right? So option B is ruled out. Each black node has two black children, but increasing the number of blacks is not our objective. Or so this is also ruled out. Each red node has two black children. I mean, we don't want to increase the number of black nodes, so it doesn't help us. But how about option A, that each black node has two red children? Then the number of reds is qualitatively increasing, and also we are not violating any of the properties of the red black tree. That there are red children having black parent, and of course we are not saying anything about uh, uh, violating the color of the root node or the leaf nodes. So therefore, option A is the correct answer. All right. Yeah, as you can see, option A is accepted. Is there any questions on this? Okay. So we'll go to question number 3. So if you have watched this video, lecture 14, Van Emde Boas data structure, then you will know that the abstract data type on which Van Emde Boas tree performs operation is one of these options. So I'll give you a minute to recall what you have seen in the video. Option C is correct. You are right. So Gahan is saying option C. So you've seen that there was a primary array, and on top of which some blocks have been defined. So that's what is called an associative array. Yeah, Greva is also correct. Associative array is correct. So that's what we have seen. It's primarily an array, but on top of which some more things have been defined like blocks, and then some is empty parameter, max parameter, these things. So this is called an associative array. So answer is C. Okay. So this was what? This was answer is A. This was also A. So now we'll look at the next question. So what is the space complexity of a 2D range tree? So if you have seen the video on computational geometry, that is lecture number 13, then you will be able to answer this question, that what is the space complexity of a 2D range tree? So I'll let you think about it for a minute.
Sir, it is option B, O n log n.
Okay. Who is this?
Sir, I agree, was.
Right, right. Okay. So can you give a sentence or two why it is option B? Just your understanding why, I mean, based on what logic you're saying that it is option B.
So the main tree of 2D range tree is balanced, we can see, sir. Like the space complexity is always given as O of n.
Yes, I'll write it down. The primary tree in a 2D range tree is balanced, or rather it's a BST. It's a, yeah,
It's
let's
a
call it.
balanced
It could be
tree, sir.
anything. It could be a BST or APL tree, red black tree. And this is the primary tree. So this takes space order n. Now there are some secondary data
Yes, sir.
structures.
Yes, sir. So since the
So,
main tree is balanced, like we can take it as O, like we can take it as O of log n. So therefore it becomes O n log n.
okay.
Yes.
So at each node of the primary tree, we have another secondary tree. Okay. So how many nodes are there? There are n nodes in the primary tree for n keys. Now, in each of these nodes, there's another secondary tree. But what is the size of each secondary tree? Is it log n? Is it order log n? Okay, so maybe I will just slightly zoom out. So it need not be log n. So the size of each secondary tree need not be log n. So what happens is this primary tree is generally, the primary tree is built on the x coordinates of the n points, n input points. And now at each node of the primary tree, you have a range of points. So now you look at the y coordinates of these points for each node. So there could be many points concentrated in one node, that is possible. But overall, the average number of points per node, that is actually order log n. So that I will write. So I'll be precise. So what happens is each point appears in order log n secondary trees. So it's a reverse counting. So you're asking that, okay, fix a point and you scan the tree, the primary tree, and check in which of the nodes of the primary tree this point has appeared. So if you know that each point appears in only order log n nodes of the primary tree, then each point appears in at most order log n secondary trees. Okay. So this is because uh, so hence the total number of elements across all secondary trees is order n log n. So every point has appeared at most log n times. So there are n points. So if you consider the sum of the copies of all the points, and the total number of copies is n times log n. So that is why the total number of elements across all secondary trees is order n log n. That is the total space occupied by the 2D range tree. So therefore, we will choose option B. So we'll see option B is correct. So what is the time complexity of finding a node in a red black tree? So if you have watched lecture number 11, then you know how to answer this. So you have a red black tree, which is a balanced binary search tree. Let us say there are n numbers in the tree, and then somebody gives you a particular number. So let us say somebody gives you a number 45 and asks whether this number is existing somewhere in this red black tree. So if it is there, then you traverse through the red black tree and find the position of 45. That means you have to tell the traversal path that, okay, first I start from the root, then I go here and there, and finally I reach 45 by following this path. If it is not there, then you simply say that 45 does not exist in this red black tree. So how much time will it take? B. Why is it B? So Gan is saying B. May I know why it is B? A single sentence. Yeah. So it is a binary search tree, but on top of that, it is balanced. It is not skewed. It is not like a path. It's more like a complete binary tree. So since a red black tree is a balanced BS tree, balanced means height balanced. Therefore, its height is order log n. So then what is the expected path length that you have to traverse? It's log n. So root 2, any leaf will be order log n, not in expected, in like absolute terms. So therefore, the running time of finding a node in this red black tree will be order log n. All right. So I hope that you have seen the video on dynamic programming. So in the video on dynamic programming, we have seen this problem called longest common subsequence. So you have been given two sequences. So string 1, I'll call it, let us say S1. S1 is this string. What is it? PQ R S T P Q R S. And another string is PRAT PBR QRPS. These two things are not of same length, I think. So this is how many characters? 4, 5, 9 characters, and this is 4, 4, and 3, 11 characters. So this need not be of the same length. Then what is a common sequence? First, let us understand what is a common sequence. So you consider a character which is common to both, then that character is common character. Now, subsequently to that common character, if there is another character which is also common to both, need not be consecutive, then these two characters together forms a common sequence. For example, the first character is P in both S1 as well as S2. So P is a common sequence. I can see that there is a Q here after P in S1. There is a Q here after P in S2. So PQ is in fact a common sequence. Okay, so we understand now what is a common sequence. So the question is, what is the longest length common sequence, subsequence? Let's call it subsequence instead of sequence. All right. So you have to understand this DP. So I'll give you a minute to think about it. For convenience, let us call these two strings as X and Y. Okay. So we'll define C of I comma j as the longest common subsequence, in short LCS, of xi and yj. So where xi is the first I characters of x and yj is the first j characters of y. So if you want to find the longest common subsequence of xi and xj, then that longest common subsequence we denote it by ci comma j. Okay. So now we have to write a recurrence for ci comma j so that we can apply the dynamic program. So what is the recurrence? So the recurrence is so the recurrence has two parts. So ci comma j is equal to c I minus 1 comma j minus 1, okay, plus 1 if the ith character of x is same as the jth character of y. So that means you have found a match. The last, so you're looking at xi and yj. So the last characters have matched. So that means you can count 1 and remaining things you can solve recursively. So c of I minus 1 comma j minus 1 you have to compute. So we do it bottom up. So we assume that ci minus 1 j comma j and I minus 1 is known. Then we only check whether xi is equal to yj. Of course, we have to define a base case. This is one part of it. The other part is see if they're different, xi is not equal to xj, then it is the max of two things. It's a max of c I comma j minus 1 and c of I minus 1 comma j. Why is that so? is not equal to. So this is because you know that at the last character there is no match. So you either consider the full of xi and yj minus one character, or you consider full of yj and xi minus one character and find the solution. So this is the recurrence for the longest common subsequence which we can use to design a DP, dynamic program, for this problem. Okay. So now what is the base case? So what is the base case? The base case is y. So let's say we're looking at two empty strings, 0, 0. So indexing of the character is starting at 1. Okay. So xi means is the first I characters of x. So what is C00? There's no match at all, 0. Similarly, you can say that C10 is also 0. It's no common thing. C01 is also 0. All right. Yeah. So this is the base case. So now you can solve. Now you can solve. And if you have solved, let me see if you have answered anything. In fact, you can try solving this. I'll give you a minute. So currently saying option D. Why is it option D? So what is the common subsequence of length 6 as per your answer? Hmm. So you're saying option D. So you have identified. Okay. So you are saying that the answer is PRT QRS. Okay. So if you apply this algorithm, you will get some answer. Have you applied this algorithm? So I'll try to identify solved using the table method is okay. You've seen the video. Okay, let's do this. So I'm going to make it bold. So P and P are common. So I'm not going to apply this algorithm. You can apply this algorithm, but we are going to verify whether this is true or there is a larger length. That means length 7 common subsequence. So PR are common. Then we have T. T is also here after R. Then we have P. We also have P here. Then we have Q. Q is here. Then we have R. So R is here. Then we have S. S is here. So how many common characters we can see? P, R T P Q R S. So 1 plus 2. So 1 plus 1 is 2 and 5 consecutive things 7. So what you have said is P R T Q R S, but one P could be added here. That is my feeling, right? So there is a length 7 common subsequence, but is there a length 8 common subsequence? So if we do this algorithm, if we execute this TP, then we will convince ourselves that we have exhausted all possibilities. And what we will report is the C of what is the length of the first uh, string 7. So you have to report C of 9, comma length of the second string, that is 11. So in C of 9 comma 11, we will find the final solution, and it is taking into account exhaustively all possibilities. So that will come out to be 7 if you go step by step. All right. So we will choose the answer as C. All right. Any doubts? So an amortized analysis guarantees what? It guarantees that the average performance of each operation is something. In the best case, the worst case, the average case. So we have seen amortized analysis, right? So we've seen that multiple operations are performed, and we claim that, what do we claim? We claim that the time complexity of each operation on the average is something, right? But do we mean in the worst case, or in the best case, or in the average case? That is the question. So you have some operations. Let's say you do push and pop on a uh, stack. And then at some point you have to increase the size of the stack. That requires you to do more work. But you want to say that the average performance of each operation is something. In the worst case, so we have seen that. So in the worst case, average operation takes so much time. That's what we have seen. So here you can see that the accepted answer is B, that the amortized analysis guarantees the average performance of each operation in the worst case is something. So we'll go to the next question. So if you have watched this video on Van Emde Boas data structure, then you would know that what is the time complexity for deleting a key from this data structure. So what is M, capital M? I'll write it down. So capital M, oops, what happened? Is the size of, what is the problem? Capital M is the size of the universe. Right. Okay. So the universe that we are considering, capital M is the size of the universe that we are considering. All right. So how much time does deletion take? So you are saying it is option C. So what is option C? It's constant time. That would be very nice to have constant time. But why is it constant time? Zero. Just need to make the element of the array equal to 0. But it has to be accessed also. The element needs to be accessed. Or rather the in, yeah. So we need to identify the position of the element in the data structure. So how much time does accessing, or rather identifying the position of the element will take? It's not a single array. If it is a single array, then what you are saying is right. I ask you to delete 45, you go to the 45th index and set it to 0 instead of 1. But you know that the blocking has been done. So you know how the single array has been divided into many blocks. So because the widgets, blocks are called widgets, are formed out of the single array, primary array. Identifying the correct widget will take some time. Super constant time, more than constant time. Okay, take time. Yeah, makes sense. Order m factorial means exponential time. Log m factorial is like log 2 to the power m. So that is like order m. So that doesn't make sense. So yes, so some small amount of time will be required. And therefore, as you have said, A and B are so large. The answer is D, order log log. So log of log is like unusually small, very small, m time. That is the answer. So we have only two questions left. So at this point, we can take a break or we can finish the two questions. So would you like to take a break or we will finish the last two questions also? Okay, let's take a break. So we'll be back at, let us say, 7:05 p.m. So we are back again. So what do you think about question number 9? So I hope you are able to see the screen. So you know how to find the longest common subsequence between two strings using this dynamic programming algorithm. So first I'll tell you the running time of the dynamic program is order how much? Any guesses? What is the running time of the DP? So suppose the length of the two strings for which you are finding the LCS is order n, both are of order, then the running time of the DP is order how much? Yeah, you're right. Because you have a recurrence which is like this. So for I you have n indices, the length of x is n. For j also you have n indices, so length of y is also n, order n. So how many entries in the table will be there? So n into n square entries. So computing per entry is nothing but checking something from the table which is already computed. At best, you add one to it or you compare the two, take the better of the two. So in constant time, you can compute an entry in the DP table. Table size is n square. So therefore, n square into constant is n squared. Yes, n squared is the time required for the DP to compute the longest common subsequence. But in the worst case, like if you're doing the brute force algorithm, then what you do is you have a string of length n, let us say, another string of length n. So you try all possible substrings. So for a string of length n, how many substrings are possible? Yeah, go ahead. Ashwini. For a string of length n, how many substrings are there? There are 2 to the power n substrings, because for every character you may or may not take it, giving two options. So 2 into 2 into 2 till n, 2 to the power n substrings. Okay. So now you have 2 to the power n substrings of one input string, again 2 to the power n substrings of the other input string. You, for every pair of substrings, you check whether they match or not. Yeah. So the running time is, overall running time is order 2 to the power n times 2 to the power n. So the order 2 to the power 2n. 2 to the power 2n, n plus n. There is 2n. So that is exponential time, right? Is that fine? We'll move to the next one. This is the last question of the day. So it is saying that which of the following is not a property of red black trees? Coming from the first lecture, every node is either red or black. Is it true? So option A. Option D is correct. That's Gan is saying. So every node is either red or black. That makes sense. That is the property of red black tree. So A is not the right option. Okay. How about the root and leaves are black? That is also true. So therefore B is also not the right option. If a node is red, then its parent is black. That is also true. That is a property of the red black tree. That if the node is red, then its parent must be black. So therefore all these options are incorrect because all these three are properties of the red black tree. So which of the following is not a property of the red black tree is answer D. So you'll say that D is the correct answer. So thank you. This is all the questions for today. If you have any questions, you can let me know. Otherwise, we'll close the session for today. So we'll meet again next Tuesday. So that will be the week 4 session. And after that, there may be an additional problem solving session that is it will be generic. So if you have any doubts, you can ask me, or I will discuss something interesting in the last session, which will be after the 4th week, an additional session. It could be 1 or 2 hours depending on the interest of the students. So we will get a notification about it. We will announce it on the NPTEL course webpage. All right. Okay. Then since you have no questions, nothing, then I thank you once again for joining, and I will see you again next week. Take care. Good night.